Our speaker today for the Math Interest Group is Bill Hery, giving a talk on Gödel's Incompleteness Theorem. Just a little bit of broad overview. Gödel wrote only a few papers, but those that he did write had a profound implications in mathematics. Gödel's study started in theoretical physics, but progressed into mathematics and then mathematical logic. His dissertation at age 23 established the completeness theorem for first-order predicate calculus and showed that a standard proof system captures all valid references. This is something most people don't bring up because it was a completeness theorem. The terminology and associated statements are closely aligned with foundations of compiler theory as far as I can see. So far, so good. After doing some important work on set theory and making seminal contributions to proof theory, in 1931, he stunned the world with his two incompleteness theorems. Briefly summarized, these state that every formal mathematical system includes the arithmetic of integers, and has a properly formed statement which can be neither proved true nor proved false. So these theorems threw a monkey wrench into two foundational programs in mathematics. So one was logicism, and the other one was Hilbert's program, by which Hilbert hoped to neatly tidy up mathematics. The proof of these theorems use a notational system unlikely to be familiar by the majority of our members, and it would take a semester's graduate course to adequately delve into all the details. It would also take an excursion into Robinson's arithmetic, Peano arithmetic, Gödel numbering, and so on. So the proofs, therefore, will not present it. However, as it was mentioned in the announcement, Bill will cover the concepts, the historical perspectives, and questions like why mathematicians even considered questions like this. What is the context in which these theorems were proven? What are the implications for mathematics, science, and philosophy? If a statement cannot be proved false, does it mean it's true? Bill will also go into detail about Gödel's work and life. And, Bill Hery is a guest speaker to both the Old Guard and the Math Interest Group. He has worked at AT&T Bell Labs as a retired professor at NYU. And he's given a talk here before on blockchain and is one of the most knowledgeable person in mathematics I've spoken with. So please welcome Bill in giving his talk on Gödel's Incompleteness Theorem.
Okay, hello to everybody. First, let me share my screen. Is that all set up to do? Okay, there is my screen. And I'm Bill Hery. I'm going to be speaking about the history and context for Gödel's work, not the details of the work itself. Okay, in 1931, Austrian mathematician Kurt Gödel proved in very simple terms, I'm not going to get all the technical niceties into this talk, and I don't want to spend time on that. He proved that every formal mathematical system that includes the arithmetic of the integers, it's got to include the arithmetic of the integers for his theorem to hold. So there's other axiomatic systems that don't have the integers. His theory doesn't apply there, even though there could be similar theories, similar theorems there. Okay, so every system, mathematical system that includes the arithmetic of the integers has a properly formed sentence, and that's a loose term I'm using rather than the proper terminology, that can be neither proved true nor proved false. There are proper terms for exactly what counts. It can't be a random collection of symbols. It's got to be something that almost makes sense in a syntactic way as being something you could even talk about whether it's true or false. So he proved there has to be a statement that's neither true nor false, or can't be proved true and can't be proved false. Actually, let me just go back. Let me give you some background on my interest in Gödel's theorem. I first encountered Gödel's theorem as an undergraduate math major in a course, or actually as an independent studies course on set theory and logic, the culmination of which was a discussion of Gödel's theorem. I don't recall that we actually proved it. It was over 50 years ago, so maybe we did, maybe we didn't. I don't think we actually went to the proof. The technical background you need and the mechanism of the proof really takes a long time to go through. So It was more the spirit of what it was. I found it very interesting, but I did not direct my mathematics career in that area. I was really interested in topology and stuck with topology until I left and went to Bell Labs and things like that. But I continued to follow things about Gödel's theory. I periodically come across articles and cut them out and save them and read them. And in the last few years, I read a few books about Gödel, the work he did, et cetera. And some of the references were listed with the announcement, and I will provide a shorter list of just the references that I actually used. But I maintained an interest and recently read a couple of biographies of Gödel. So when Walt was talking to me about trying to find a topic that I could give a talk on, I don't remember which of us said Gödel. I think I might have said it first. At first, it sounded like it was kind of a daunting task. Then I decided I could do it if I talked really about the history of what led up to it and the context that he proved here, and a little bit about what comes out of it and what people are interested in about it. The questions that I want to talk about here, first of all, what led mathematicians to consider questions like this? And I'm not just going to talk about what happened 20 years before. What I want to start with is really the way mathematics has worked over the years, and that they do something and then you go into something that is a contradiction or you don't understand, and you then wind up saying, we got to get more rigorous and we've got to dig deeper and go to a lower level. And over time, that wound up getting to the level of what Gödel is doing. And I hope to show some examples of why that happened in mathematics. It's far from a completed set of examples, but at least give you an indication of why, even going back to ancient history, things wound up having to go into a deeper level. The next thing I want to talk about is what was going on in mathematics around the time and shortly before Gödel did his work. What were mathematicians thinking about? You might look at that statement and say, that seems to be just off the walls, strange thing, very esoteric, not really in mainstream mathematics. And in a sense, that's true, but mainstream mathematicians, in trying to straighten out problems in mathematics like contradictions and things you couldn't understand, they wound up going down this route. And a lot of prominent mathematicians were involved in this area at the time when Gödel was working, including John von Neumann and David Hilbert, who were two of the most prominent mathematicians from the late 19th and early 20s or early to mid 20th century. So it wasn't just a little offshoot of a few specialists that would do it. It was really mainstream mathematicians who were, if not working on it, at least recognized the need for it. Okay, what are the implications for mathematics, science, and even philosophy? I won't really talk about philosophy, but that's a topic that people can continue reading about, and I'll give some pointers. The thing that intrigued me about Gödel's theorem, and in fact intrigues mathematicians right away when it was proved, was there were famous mathematical problems that were hanging around for hundreds of years that hadn't been solved. Could it be that they were these kind of undecidable problems? The famous one when I was a student was Fermat's last theorem, and everybody was wondering, could Fermat's last theorem be something that could never be proved true or false? Was it an undecidable in Gödel's sense? That's now been solved, but there's still some others, which I'll mention later, that you wonder, is the Riemann hypothesis one of those hypotheses, et cetera. And there's the side question related to this that we'll talk about, this is going to be a discussion question. If a statement can't be proved false, does that mean it's true? That's more of a philosophical question. And I'm not going to show even an outline of the proof because it's just would be this talk and several more. Okay, a pattern in the history of mathematics is typically most things in mathematics, at least until recently when some people started doing pure mathematics just for its own sake, was basically you do something to come up with a solution to a problem, you use it, you make it better, you broaden it, you keep working on it, expand it, etc. But somehow you wind up with either inconsistencies or contradictions and you need to fix them. Or you find things that you can't figure out at all and you want to fix them. At that point, you start making things more rigorous, get more formal about things. And eventually the height of that is an axiomatic system, which is really what Gödel's theorem is dealing with. It is an axiomatic system for the integers. And that's sort of the gold standard in proof in mathematics, not in proof, but in structure in mathematics. But no matter what they've done, over the literally thousands of years, there's contradictions and conundrums that come up. And I'll start with some very early things that show the very early history of mathematics. The Egyptians understood enough of mathematics to understand about the 3, 4, 5 right triangle, that could give you a perfect right triangle if you had the sides 3, 4, and 5, or in some same proportion. And they used that for laying out the base of a pyramid. If they were like 2 degrees off, then when they built around, things wouldn't fit together. So they got very good at that. And they would do it with a piece of rope, as in the lower figure there. And they just had to understand about the 3, 4, 5 relationship, and they could take a big piece of rope as long as they needed, mark off 3, then 4, then 5, with whatever units they want, have the rope and use that. And so, that worked very well for what they were doing. The Greeks then developed a lot more geometry and was formalized by Euclid. And I'm sure you remember Euclidean geometry from high school. Archimedes used Euclidean geometry, and he actually got a very good estimate for the diameter of a circle as a measure of the radius by inscribing and superscribing regular polygons around the circle. And you can see in the figure, there's the green circle and the one inscribed, and then the circumscribed polygon. He actually went, I think, to 32, this touchscreen mouse, touchpad mouse is going to be a real problem. I'm going to minimize using the mouse. But you can see that he could just use Euclidean geometry and get very close to the circumference, the side length of circumference with that methodology. So that was another application of extending geometry. Aristotle then at the same time was developing logic, which is another basic thing in mathematics. Okay, so at some point, I'm not sure what motivated, but Euclid actually took the brilliant step of formalizing geometry with an axiom system. The axiom system is very simple. In general, an axiom system, you need primitive objects, axioms, which are things you assume to be true. You can't prove them, they're too fundamental, and some rules of inference. So in the case of Euclid, he had primitive objects being those things like the point, straight line, intersection, things that you sort of intuitively knew what they were. Small number of axioms, there were only 5. A rule of inference, which was logic related to what Aristotle was doing. And from that, he was able to build up all of the geometry that they needed. And it's amazing how minimal that base is, that he could build so much. You might know that there was a controversy about the parallel postulate, the 5th postulate, which people actually found they could take away and get most of Euclidean geometry. Euclid himself was able to do that because he doubted whether the parallel postulate was completely true. Okay, so all the theorems of geometry come from those axioms or postulates. We now call them axioms. And what that lets you do is, if you're trying to prove something, you can just keep saying, why is this true? And you keep drilling back, why, until you get down to how it comes out of those 5 axioms. So you have this basis that everything is built on. And anytime you can find a place where that basis applies, you can use all the theorems you prove. And it was a great model for mathematics. It's amazing to me in retrospect that he even came up with doing something that was this general in those days, but he did, and it's wonderful. And it was kind of ignored for about 2,000 years. Okay, but in doing all this work, they did find some conundrums, either paradoxes or things they couldn't figure out. And you've probably seen, remember these from much earlier in your education. One is Zeno's paradox, that motion is impossible. And this is one the philosophers discussed more than the mathematicians. But the basic idea is, if you want to move from point A to point B, call them 0 and 1, but just for simplicity. First, you have to move from 0 to a half, then a half to 3/4, then 3/4 to 7/8. then to 15/16. So you've got all these incremental steps as you're going along. There's an infinite number. How can you ever get there? And they never developed a mechanism for dealing with infinity and infinite processes, so they couldn't figure that one out. Another one in logic, there are a lot of forms that this is usually talked about. I think the standard one from Aristotle was something about all Cretans are liars, etc. But they all boil down to is the statement, this statement is a lie. Okay, well, if it's a lie, then it's true. If it's true, then it's a lie. Obviously, circular reasoning, it doesn't make sense. How do you deal with that? And that's a problem because of self-reference. In general, self-reference and things related to infinity were causes for problems throughout. Okay, a couple of other points that are not quite conundrums, but integers and rational numbers were easy to construct from Euclid. The Pythagoreans believed in almost a religion based on integers and rational numbers. At some point, somebody figured out that you can prove that the square root of 2 is not rational. And that, to the Pythagoreans who considered that sacrilege, the legend is that the person who discovered that was then drowned because they wanted to get rid of that sacrilege. In practice, what happened in mathematics is that, hey, this is something new that we've got to add, irrational numbers. So that was good. One more thing that I'm adding that's not really a conundrum, but is worth thinking about because we're going to come to it later. Euclid's proof of the number of primes is infinite was really very original. You've probably seen it before. I'll just talk through it very quickly. If there's questions about it, we can talk about it, ask questions later. But basically, if you assume that there's only a finite number of primes, multiply them together and add 1, that none of the primes you knew about divides that, but it's got to be factorable into primes. So somewhere else there's got to be a prime number. The interesting thing about that proof is that it doesn't show you how to get another prime number. It just says 1 has to exist. And this is probably the first proof of existence without constructing what it was. And that became an important point in mathematics more in the 19th and 20th century, where people started looking at mathematics where you didn't allow proofs of existence without showing how to construct it. There's mathematicians called constructivists who really want to try to build everything by showing you everything you can do. You want to be able to actually construct, not just say it's got to exist. And that comes in with Gödel's proof. Okay, so now let's go to the era of calculus. Isaac Newton and Leibniz developed calculus using infinitesimals to work with limits, continuity, derivatives, etc. They were vanishingly small numbers, but never 0. Okay, but they dealt with them intuitively. They were not precisely defined. Definite integrals, similarly, they were intuitively done. They didn't formally have a definition of limits, etc. And it was just a sequence of approximations that they used. Again, the infinitesimals came in, and they would be just intuitively done. In general, the limiting and infinite processes were handled intuitively rather than with careful definitions. And rules for limiting processes and how they interact with arithmetic operations were not carefully worked out. And greater rigor was actually needed in math at that point. And I'll just give one example. There's a lot of examples historically where you had problems. Well, I'll just give the simplest example I can come up with. This is a contradiction that comes from basically something very simple. You've probably seen it. That's been around for probably hundreds of years. Just take the simple statement, 0 equals 0 plus 0 plus 0, ... This is where we're fudging infinity. We're not saying exactly what that means. You can rearrange that and replace every 0 with 1 minus 1. So you have 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc., still equal to 0. Now we just rearrange the parentheses using the associative law, which you might remember from arithmetic, that basically is a plus b parentheses plus c is the same as a plus parentheses b plus c. Just rearrange the order of addition. And if you do that, then you come up with 1 plus minus 1 plus 1 plus minus 1 plus 1, etc. And that becomes 1 plus 0 plus 0 plus 0 equals 1. So you have 1 equals 0, which is obviously not a good thing. And things like that weren't clear what was wrong with that. And what it really comes down to in retrospect is that someone's trying to use the associative law on an infinite process. So we needed a way of dealing with infinite processes more rigorously so that you could say when that worked, why that didn't work. That if you just apply the standard things with sequences and convergent sequence, you'll see that what's really happening when you do the one in the middle is you're getting all, as you go through the sequence, you're going 1, 0, 1, 0, 1, 0, and so it's not going to converge. We know that now, but until you defined convergence, that wasn't really something that people would know about. Okay, so what needed was something to really create the numbers in a way that's more formal. Numbers were just done kind of informally. You knew what they were, but maybe you didn't know what they were. So what was needed, as I said, was the piano postulate, we'll talk about in a little while, that actually formalized the definition of numbers and how numbers come from basic set theory and logic. But you no longer take the numbers for granted, you prove their properties. And just as a side, any formal system that has a contradiction in it is fatal, because in a formal system that has such a contradiction, you could actually prove every statement is both true and false. And that's obviously pretty useless. Okay, another reason to be more rigorous about things is that things that were intuitively obvious in a lot of domains wound up not being so obvious when they looked at them more closely. And this happened in the 1800s. If you look at the figure below, the black line is a line that basically goes in any random direction, but it stays within a finite space and it never crosses itself. It's just called a simple closed curve. And you look at that and you say, well, it's pretty obvious that with the simple closed curve, if you go around it, let's say clockwise, everything to the right is the blue area. That is distinct from everything to the left, which is the pink area. And so this curve changes the whole, well, that doesn't change it. It splits the whole plane into 2 pieces, an interior and an exterior. And that seems very intuitively true. And people took it as being true until Bernard Bolzano, he first identified that it was needed to be true. And people were trying to prove it for a number of years. Finally, Camille Jordan was the first to give a proof of it. And that's when it got named the Jordan curve theorem, because he was the one that proved it. After a while, mathematicians kind of looked at this proof and, you know, this proof isn't really right. This thing's missing. We don't think the proof is correct. And it was considered to be not a true proof for a number of years until Oswald Veblen did the proof that was generally accepted. Mathematicians have since gone back and looked at Jordan's proof and said, you know, he really was right. But Veblen has been credited with the first real generally accepted proof. And we'll mention Veblen again a little later. But I'm putting the years of that all the mathematicians lived in parentheses so you can see what the intervals were. So you can see that Oswald Veblen, who finally did the proof, was born the same year that Bolzano, who identified it needed to be proved, died. And I don't know the exact time of Veblen's proof. I think it was in the 1920s, but I'm not positive. So this is a case where the intuition really was right, but you had to really know that you've got to dig in and really prove some of these things that might seem to be obvious. Okay, so now we can get to limits and continuity, etc. As I said, there was no real definition for limits that was being used by Newton. They just had the intuitive thing with the infinitesimals. In 1817, Bolzano, the same Bolzano, came up with the idea of the epsilon delta proof. Now, you probably, hopefully remember this from calculus. That's how you did limits, derivatives. There was this epsilon delta, and that was a formal definition of what you meant by a limit. It wasn't just an infinitesimal that you sort of knew when you could throw it away and drop it. And that was sort of the start of formalizing stuff that was done in calculus and things built on top of calculus. So he was the first one to do that. And then for the rest of the 19th century, you had a lot of other mathematicians adding a lot more to that. Weierstrass, who there was a Bolzano-Weierstrass theorem, which is important in real analysis and limit theory. Cauchy with Cauchy sequences and a lot of things in complex variables. The Cauchy integral theorem, there's a lot of that he did. Riemann, who's probably the most famous and probably the most significant mathematician of that era, he actually came up with a definition of a Riemann integral that could be formally proved, similar to the epsilon delta thing for limits and continuity. He also did Riemann surfaces and complex variables, Riemann geometry, which is the variant of Euclidean geometry. We changed the fifth parallel postulate to something else, and that wound up being the basis for the mathematical basis for Einstein's general relativity. Dedekind, you might have heard of Dedekind cuts. Cantor, who did a lot with cardinal arithmetic, infinite sets and things like that. But through all this, arithmetic was still taken for granted. It wasn't rigorous. It was like, yeah, you know what arithmetic is, it works, right? Also in the same era, George Boole, for which Boolean algebra is named, and then later Gottlob Frege, I'm not sure if I'm pronouncing that correctly, they started formalizing mathematical logic. So they took what Aristotle was doing and tried to make it more formal and almost computational. And George Cantor and Frege both developed what was called a formal version of what's called naive set theory. Naive in the sense that the sets are not defined axiomatically. They don't have an axiom system for it, but they start doing a lot of things with manipulating sets. But it's not axiomatic, but that comes later. Cantor's work was especially about infinite sets, and we'll mention that again later. But what about a formal based arithmetic? That was the one thing that was missing. And given that mathematics, so much of mathematics is based on arithmetic, you really needed that. In 1889, Peano came up with a set of postulates that is an axiomatic system for the set of positive integers, which is normally referred to as Z+ by mathematicians. And the postulates are very simple, but the point is this gives you a way of actually constructing the positive integers from an axiomatic basis. All you need is a little bit of set theory and logic below this. That's the only level lower. And the postulates, you probably have seen them before, but just go through them quickly. One is a positive integer. That's your primitive object. The postulates are that there's a unary successive function S, think of it as +1, such that for every positive integer, S of n is a positive integer. So there's a set of integers. I guess that probably should be somewhere as the primitive objects are the integers. One is an integer, and n plus 1 is also an integer. That's what S of n means. So think of it as +1. So that way you get 1, 2, 3, 4, 5, 6, 7, etc. Defined from the one before with the successive function that is part of the axiom system. And the other rules you need are if m and n are two integers that are not the same, then S of n cannot be the same as S of n. And that's to prevent you from essentially getting circular arithmetic like clock arithmetic. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, back to 1. Okay, this bars that because the successive function has to be different. And one last thing you need to tie things together is that 1 is not the successor of any integer. And this is a way to define exactly what you get as the set of integers. For an inference rule, what you have is what we call mathematical induction. If for any function f, if f of 1 is true, and in big brackets, whenever f of n is true, then f of n plus 1 is true, then f of n is true for all n. So basically you say, prove it for 1, and then if you have a general term, f of n, if you can prove that whenever f of n is true, f of n plus 1 has to be true, that lets you essentially step through the integers. It's true for 1, then it's true for 2, then it's true for 3, etc. And that induction rule is used. Again, you probably did proof by induction when you're in high school. And the beauty of this is that it's simple and it's an axiom system, but you can build on top of it with logic, and particularly with the induction rule for inference. You can actually go through and you can define what it means to have n plus m. It's actually a double induction on n and on m, and you can define it. You can get all the normal rules of associativity, commutativity, etc. You can then define zero, you define negative numbers, all formally from these axioms. And you can then prove all the normal functions of properties of arithmetic, distributive laws, inverse, etc. And you very quickly get all the rational numbers. And then you can even go further with Dedekind cuts or Cauchy sequences and get all the real numbers. And there was a book written, I don't even know when, that actually went through proving all of these properties from that definition of the integers, those axioms for the integers. And years ago when I taught real analysis or calculus, advanced calculus, whatever it was called in different schools, one of the things was to first start with proving that what the real numbers were. And I actually had the class, I showed some in class and then had the class do homework where they had to prove something like the distributive law for multiplication over addition. And you do it by induction, and they're actually all very simple proofs. The problem is there's so many things there that it takes a whole book to write out all the proofs. And nobody wants to actually read that book, but somebody did actually write a book that had all that. But notice that sets and logic are still used with the axioms and in the proof. So it still depends on set theory and logic. Okay, now what was going on in the late 19th and early 20th century, going beyond that? Okay, David Hilbert, who was the most prominent and the most influential mathematician in the late 1800s to the early 1900s, he began a formal program in 1899 to try to formalize all of mathematics as being built up from things like the Peano axioms and other axiomatic systems. And so he was pushing for that. And he's going to be going on with this kind of stuff for another 30 years or so, actually more than 30 years. Then along came Bertrand Russell and Russell's paradox. Now remember, the Peano axioms are based on using set theory. They are based on sets. So set theory is important, and now we get to come to the realization that set theory has to be formalized and axiomatized because of Russell's paradox. Okay, at the time Russell did this, a set was just used vaguely from any collection of objects. Didn't matter what they were. Then Russell came up with the paradox, again, which a lot of you have probably seen. I said, let R be the set of all sets that do not contain themselves as an element, not as a subset, but as an element. And virtually every set you think about would be one of those, because when is a set an element of itself? And you have to work hard to try to come up with a case where one would be. But you look at the set of all sets that does not contain itself as an element, then you ask the question, is that set R a member of itself? Well, if it's a member of itself, then by its definition, it's not. And if it's not a member of itself, then it has to be by definition. So this is clearly a contradiction in naive set theory. And this caused major problems because people depended on set theory and all of, it's the basis for mathematics. How can you have a contradiction in it? And again, it's a question of self-reference. Just like the Lawyer's paradox in the same category of problems. So it showed that you needed a solid basis for set theory, an axiomatic basis. You can't just let set be anything arbitrary. It's got to be somehow constrained. And so in the early 20th century through the 1920s or so, there was a lot of, especially in the 1920s, there was a lot of work to axiomatize set theory. Basically, what they had to do was find ways to get rid of things that are too big, so you eliminate the self-reference things. And so what they had was not just this rule that a set is any collection of objects, but they had axioms about what a set could and couldn't be. And There were several different approaches to that. Russell and Whitehead wrote a book called Principia Mathematica, in which they came up with an axiomatization of set theory and tried to build up all of mathematics formally. And it was a huge, very dense book that came out between 1910 and 1913. They went beyond sets, and they had classes, and they had, so you could have things that were sort of like sets, they called them classes, and they weren't sets, and they had a whole hierarchy of things like that. And it was, according to John Kemeny, who was a famous mathematician, he was Albert Einstein's assistant when he was a graduate student. He said it was the book that was most talked about and least read, because nobody would actually sit down and read it. I've know about it, I've never tried to read it. So that was one attempt. The one that is commonly accepted today was done by Zermelo and Frankel, and it's referred to as ZFC, and I'll explain the C a little bit later. That's the basis that most mathematicians use. Most mathematicians don't actually use these set theory axioms directly. They actually use the C part of it, but they assume they're working in that space. The third one was the one from von Neumann, Gödel, and Bernays, which is similar to ZFC. I don't know offhand what the details of the differences are, but you can see some famous names connected to John von Neumann, who you know from game theory, various topics in mathematics, computer science, building what is arguably the first stored program computer, etc. Gödel we know about, and Bernays, who was a famous logician who was actually Hilbert's assistant. Okay, so we had those things come about, and the ZFC is, as I said, commonly accepted by most mathematicians. Some don't want to accept C. But in developing that, two things came up that are worth talking about because they become significant later, particularly for Gödel. One is the axiom of choice, which is something that unless you've really studied mathematics, you might not have heard of before. This actually comes from Zermelo, who is of the ZFC. It is another one of these things that is so obvious you don't think about the need to prove it. And then you think about the need to prove it and you say, wait a minute, what am I going to do about this? The axiom of choice is very simple. Suppose you have any collection of non-empty sets. You want to create a new set that has just one element from each of those sets. Well, if it's a finite set, that's fairly easy to do. But if it's an infinite set, what lets you do that? There's nothing in the axiom of set theory that would let you go to an infinite number of sets to build a set, another set that has one item from each of those sets. So this became a major problem for what to do about that. And mathematicians wanted to assume that it was true. It's called the axiom of choice. And a lot of mathematicians wanted to assume it true because it turns out that even when you go higher up the mathematical chain into applicable or even applied mathematics, there are a lot of theorems that you want to prove using that essentially the axiom of choice. And it was done before without people thinking about the fact that maybe this wasn't so clear. So the axiom of choice became a controversial thing. Do you include that in the axioms or not? How does it fit in with the other axioms of set theory? The other one that is somewhat important, and I mention it mostly because Gödel also was involved with this, is Cantor's continuum conjecture. That's the way Gödel referred to it. Basically, I don't want to go into details, but there are different sizes of infinity when you, in terms of this, the size, the number of elements of the set. There's the number of elements in the integers, which turns out to be the same with the proper definition of cardinal numbers as the number of elements in the rational numbers, okay? Cantor proved that if you look at all real numbers, they have to be more real numbers than integers or rational numbers. So that was two different sizes of infinity. The question was, is there anything in between? And Cantor's conjecture was that there's nothing in between. So that became another interesting question when you're dealing with set theory. Both of these things, in your axiomatization of set theory, you really have to think about and straighten out and decide what you're going to do with. And we'll come back to them later. Okay, so what do we expect from an axiomatic system? Okay, Hilbert's program had 3 key points. Okay, so we're looking now, this is really talking about axiomatic systems in general, but mostly he had the systems that include the real numbers or the integers, which then leads to the real numbers, etc. First, you wanted consistency. A mathematical system is consistent if there is no sentence that can be proved both true and false. If you can prove one something is true and false, as I said before, it's useless. You can prove everything is true and everything is false. So that was the primary concern of the Hilbert's program and of mathematicians in general about any axiomatic system. The second was completeness. Every properly formed sentence, again, I'm using the vague terms here, not the proper terms, can be either proved true or proved false. So every statement that is of the right syntactical structure has to be either true or false, and you can prove it. Okay, and this was something that Hilbert was very insistent on, and he felt mathematics was complete, and therefore you had to be able to do this. And that was his goal, was to find a way to prove that. And he originally was talking about this in the late 1890s, and was still talking about it in 1930, or 1928 at least. The second is decidability, which sounds almost the same as completeness. Completeness says that every properly formed statement can either be proved true or false. Decidability says that there's an algorithm to decide if a properly formed sequence is true or false. So that's different. So one just says it has to be true or false. The other one says there's a way to actually figure it out. And the algorithm might take billions of years to work, but there still has to be something. So those are the 3 things that he was concerned about in any axiomatic system. And something that's sort of implicit is you want enough axioms that you prove what you need. So that comes down to, like with Euclidean geometry, if you're working on a plane, you want that 50 parallel postulate because that's what lets you do it on a plane. But if you're doing geometry on a different surface, then you want to replace the parallel postulate with something different. And you don't want to add any axioms you don't need, partly because it sort of violates the idea of this minimalist nature of the axioms. You want to make sure every axiom is really needed. Plus, if you add more axioms in, then you might be adding a contradiction. So you don't just throw in a new axiom randomly. Okay, so more about Hilbert. He is, as I said, the most influential mathematician of the late 19th century and the early 20th century. He was active pretty much until his death in, I think, very early 1940s. He made significant contributions to the foundations of math. This is what we're talking about, is foundations of math. He made contributions to pure math and to applied math and even mathematical physics. So he was really all over the place and made very significant contributions in all those areas. You've probably heard of him for 2 things. One is Hilbert space, which is one of the fundamental things in functional analysis that's used as the basis for a lot of work in all kinds of mathematical physics, etc. And most famously, probably his 23 problems that he posed the challenge to mathematicians in 1900. Okay, so I'll go to some of those questions in a minute. In 1930, he added a challenge to mathematicians to prove that piano arithmetic was consistent, complete, and decidable. So there's 3 things that he'd been talking about literally for 20 odd years. He said in 1930, we've got to get mathematics. This is another challenge to mathematicians because they hadn't answered everything before. But so he wanted those 3 features. And I just throw in a quote that I like because I like it. It doesn't really fit in with the talk. In that 1930 radio speech, he said, the instrument that mediates between theory and practice, between thought and observation, is mathematics. So as a mathematician, I like that statement. Couple of comments on Hilbert's problems. Of the 23 problems, 8 are solved fully, 9 are partially solved, 4 are completely unsolved, and 2 are deemed too vague to really say whether they're solved or not. One of them was essentially saying, we need to figure out more about calculus of variations. Well, yeah, more was figured out, but does that solve the problem? He didn't really have a specific problem. But it's worth noting a couple of the problems. problem one was to prove Cantor's continuum hypothesis. So he's identifying that as a major thing in 1900. And the solution, which we'll talk about a little bit more, basically between Gödel's work and somebody named Paul Cohen in 1966, they proved that it's actually independent. That you can't prove it true and you can't prove it false. So it is essentially one of these Gödel style sentences that you can't prove true and you can't prove false. So we'll talk about that a little more. But that was important enough that when Paul Cohen did his half of that to finish the problem, he got a Fields Medal for it. Problem number two, prove the Peano axioms of arithmetic are consistent. Well, Gödel wound up proving that it can't be proved from within arithmetic that they are consistent. And somebody else who I'm not familiar with, Gensen, proved that it is consistent with some outside arguments. But Hilbert was talking about proving everything within the system of arithmetic. So that was one, that he was talking about for a long time and was proved false. Two others that are just interesting in general. Problem 6 was axiomatization of the laws of physics. Now, this was in 1900. This was before relativity, before quantum mechanics. So it was a much simpler problem then, but over time, Hilbert, von Neumann, and Kolmogorov and others did a lot to do that, even getting into axiomatization of the laws of quantum mechanics, or the mathematics behind the laws of quantum mechanics. And so that's another area that von Neumann did a lot, and Hilbert did some. I don't know exactly how much. And the last one I'll mention, because it's still one of the famous unsolved problems, to prove the Riemann hypothesis, which is complex to describe, so I won't do that now. But Goldbach's conjecture, which is one of the simplest open conjectures in math, it just says that every even number greater than 2 is the sum of 2 primes. Simple to state, simple to check for specific examples, and I'm sure they've checked for up to millions of digits long. Nobody's found a counterexample. Nobody has come close to proving it. And the third problem was the twin prime problem, which says that, okay, there are twin primes that differ by 2. So they're almost next to each other. So like 11 and 13, 31 and 33. And you've got, there's a lot of them. It is still not known if there are an infinite number of twin primes. So he's mentioned all 3 of these in problem 8, and they're all still unsolved. Okay, so now let's go on to Gödel. How am I doing with time? Okay.
You're okay.
Yeah, well, no, there's a lot more. Okay, so Gödel was born to an Austrian/German family in ruined Austro-Hungarian Empire in 1906. After World War II, this became Brno in Czechoslovakia. He never learned Czech. He considered himself an Austrian. The biographies I've seen seem to say that the parents actually, they just say they were German, but they were living in what became, well, what was then Austria and became Czechoslovakia. His family called him Herr Warum, Mr. Why, because from the beginning, he was always asking why, and we did another why, deeper, deeper, deeper. So we always tried to dig down to the most fundamental things. When he went to University of Vienna in 1924, he started as a physics major because he thought physics was fundamental to the world. Then he realized that mathematics was fundamental to physics. So he went on to major in mathematics, initially in number theory, and then moved to the foundations of math. Along the way, he also studied some philosophy, and he was influenced by philosophy. He was always looking to do the most fundamental things, not add more details higher up the chain. Okay. During his student days, he was a relatively passive member of something called the Vienna Circle. You'll find this a lot, and when you read books about him, I'm not going to do much about it, but the biographies typically have a lot of space devoted to that. The Vienna Circle was an informal discussion group that was mostly about philosophy, and particularly the philosophy of mathematics. What is truth in science? Even some things about mathematical economics, but it was really always with a philosophical bent, not trying to prove things. And there were debates about when you could accept something as being true, as a mathematical or a scientific fact. One of the members, one of the things that a lot of them thought was that until you had some kind of a representation of it that you could look at and see was true, and you could observe it with your senses, something wasn't true. So one of the members was Ernst Mach, who was an older gentleman by then, and he's the one that Mach numbers are named after. He refused to believe Einstein's general relativity until it was demonstrated to be true in an observation in 1919. So that was the kind of thing they debated. Is mathematics discovered, or is it invented? A lot of stuff like that. They had people in the group from all over. They would have visiting people. They also were very widely read, and they had members of the group actually took Russell and Whitehead's Principia Mathematica and Ludwig Wittgenstein's work on logical positivism presented the group. Logical positive actually was the philosophy of science that ran contrary to Gödel's methods, but most of the people in the Vienna circle actually believed. That was where their belief things were. So Gödel was at these meetings, and from what I've read, he never said very much in it. He was not in agreement, but basically didn't say very much. One of the references goes a lot into the philosophy that they were talking about and how it differed from Gödel, etc. I'm not going to get into that because that would be a whole separate talk. Okay, so Gödel has been hanging around with this group from, I think, about 1924 when he first started college there. But in 1928, the full Hilbert program is presented. That's when he wants the completeness, consistency, and decidability of arithmetic. And by extension, if you do it for arithmetic, meaning the piano accent, it goes then to all things in real numbers. It goes to differential equations, calculus, all the things that are built up on that. So it's really, a lot of mathematical physics is all covered by this, that he wanted completeness, consistency, and decidability for. And a lot of mathematicians were working on this program at the time, many prominent ones. I'm only going to mention the prominent ones I know. I'm sure many others were. But John von Neumann, you see, he was working on set theory, and he was actively trying to prove the consistency of piano arithmetic. Gödel was obviously working on it. Alan Turing started working on these things, particularly the decidability, starting when he took a course in foundations from Max Newman, not Neumann, in Cambridge in 1934. And 2 years later, as we'll see in a minute, he proved that decidability couldn't happen. Alonzo Church at Princeton was also working on things about decidability. And Paul Bernays, again, Hilbert's assistant, he was working it. Note that von Neumann, Turing, and Max Newman all became seminal figures in the development of computers. Max Newman is not as well known because what he was doing, which was sort of parallel to what John von Neumann was doing in Princeton, he was doing a classified environment, and it wasn't known to the public for a number of years. So they both can sort of be credited with arguably the first stored program computers, but one was classified and unknown. They didn't know what each other was doing. Turing was actually helping Max Newman for a while until his security clearance was taken away. Okay, so back to Gödel. In 1929, he proved the completeness of first order logic in his PhD thesis. Okay, so it looks like he's going along with Hilbert's program. That should be part of it, even though it's the logic, not the arithmetic, but that underlies the arithmetic. Then the shock came in 1931 when he presented a summary of his incompleteness theorem. There are actually two. He printed the summary of the first at a conference in Königsberg, Germany. Okay, and he proved in that that completeness was impossible. That's the famous theorem. And his first presentation was at a conference. He just read a paper. It was on the last day of a conference. Hilbert and von Neumann, both at the conference, Von Neumann went to Gödel's talk, Hilbert didn't. Von Neumann said, wow, this is really great stuff. He recognized that it was important right away. And he thought about it, and then he sent a letter to Gödel a few weeks later saying, not only does your work prove that you don't have completeness, there's also a way to take what you were doing and show that you don't have consistency. Gödel wrote back saying, yeah, I know that it's in the paper I'm writing. I didn't have time to present it at the conference. Von Neumann, being the gentleman that he was, said, okay, it's yours. I'm not going to publish it ahead of you. And he just became a huge supporter of Gödel's work for the rest of his life. Okay, so in 1932, Gödel's paper on incompleteness is published. It hit the world. The first theorem proves that arithmetic is not complete, and the second proves that the consistency of arithmetic cannot be proved within arithmetic. Two of Hilbert's main goals are shot down. Oops, that's it. Hilbert wasn't very happy, obviously. Okay, some of the immediate reactions. I'll give some of positive reactions, negative reactions, and just how it might affect a working mathematician. Von Neumann recognized the brilliance of his work, and he spread it. He went back to the Institute for Advanced Studies in Princeton, where he was a faculty member. I'll do a digression on IAS in a minute. Gave talks about Gödel's work, and he helped arrange for Gödel to get membership at IAS. But he then said, okay, that area of math, the most important things are already done, and he went on to other things, other areas of mathematics, and eventually the work with computers. But a sidebar on Institute of Advanced Studies, for those who are not familiar with it, it is a private research institution. It is in Princeton, New Jersey, and closely affiliated with, not even affiliated, they work with Princeton University math department, et cetera. But they're independent. They have their own building, and they have two kinds of memberships, they call them. One is faculty, which is a permanent lifetime appointment. They have to do no teaching. They don't have any publishing requirements. They just have a lifetime place to sit and do research in peace. And when it was formed, von Neumann and Einstein were two of the first people that were invited in. The first mathematician actually was Veblen, who proved Jordan's curve theorem. So that was a permanent membership. There were also what we would now call visiting positions, typically for 1 or 2 years, that were meant for young mathematicians to have a chance to just do their research in peace and work with and talk to other prominent mathematicians. So what Gödel got was a temporary or visiting membership. Okay, so that was von Neumann's reaction, was very positive. Hilbert, according to his assistant Bernays, he became angry when he heard of the results, but eventually accepted it. He did include the proof in a book on foundation of mathematics in 1937, but he didn't include it in any of his actual work itself. And he wrote some things that are hard to decipher, basically saying he still thinks that you can prove or disprove any sentence. And I can't make sense out of the wording that I read, how he sees that's true given the proof, or accepts the proof. Wittgenstein is another extreme. He just thought his work was inconsistent with his own philosophy of mathematical foundations and just called it logical conjuring tricks. So he ignored it with the rest of his work. As for just working mathematicians not in that area, Hermann Weyl, who was also one of the first 5 mathematicians at Institute of Advanced Studies, he said later on, not at the time, it was a constant drain on the enthusiasm and determination with which I pursued my research. So it was discouraging for me. He says, you're working on a problem, even if you don't get to solve, you want to at least think it's achievable at some point. And he could work on a problem that there's no solution to. So he was sort of disturbed by it, but looking at his mathematical output after, he was still doing significant work all the way until the 1950s. So it didn't affect him that much. Okay, I'm going to skip a lot of this just in the interest of time, because I want to leave time for discussions. Basically, the important things here are that Gödel goes back and forth to Austria a few times. Some strange stories that go with that are in the biographies. The important thing is that Alan Turing using his Turing machines, and Alonzo Church using his lambda calculus independently proved that arithmetic is undecidable. That's the end of Hilbert's program. All three of them are done. Gödel wound up staying on and off at IAS with visiting positions until 1954, I think it was, when he finally got a permanent position. But he did continue to work, and he did significant work. In spite of what was in the blurb that Walt read, there was a lot more than just his work on that he had that was published. In particular, he published work on the axiom of choice and the continuum hypothesis that proved that both of those are consistent with the fundamental theorems or axioms of set theory, namely ZFC or ZF in those days. Okay, so that was halfway to proving that they were undecidable problems. And I'll talk more about that in a minute. So he's back at IAS. He famously in 1940 formed a close relationship with Albert Einstein. This is when he stopped going back and forth to Austria, and he just stayed in Princeton. And there's a lot written about their friendship. There's two photographs of them together. The one on the right is a photograph that was posted by IAS that is clearly a scan of one of the photos they actually have in their archives from the early days. And the one on the left in color, I'm not sure when that was taken. Gödel looks younger, but it is a color photo. I'm not sure when that was. But what I like about that photograph is that it's the only photo of Gödel where he seems to have a real smile on his face, as does Einstein. All right, I'll include this anecdote because it's too funny to not include. In 1946, he was being driven to his final swearing in as a US citizen in Trenton, and he was being driven by Oscar Morgenstern, who was a famous economist who wrote The Theory of Games and Economic Behavior with John von Neumann, and Einstein. They were going to be his witnesses at his swearing in. He starts talking to them about the fact that he found a flaw in the Constitution that would enable a dictator constitutionally to take control of the country. And he actually started mentioning to the judge, but the judge just shut him off and said, you're a citizen, goodbye. That was only documented much later by Morgenstern in some notes that were only came out in, I think, 1989, something like that. But he did not say what the flaw was. So constitutional lawyers have tried to look and see if they can guess what the flaw was that he found. Nobody's identified what it had to be. There's a few speculations. He also published an alternate solution to the Einstein's equations for general relativity that allows for time travel. Not that he believed it, but it was another solution to those equations. And as in many things in science, there can be different solutions to the same set of equations that have different interpretations. And these are just more or less some of his honors. He did leave a lot of unpublished papers in his notes. His notebooks are all in the possession of the Firestone Library at Princeton University, not the archives at IAS. A lot of the things that have been published, in some cases, he didn't want to publish things because he felt like his work wasn't particularly accepted and appreciated, so why bother? It was like they didn't think it was important. He thought it was. And some of the stuff has been shown to be important. He also had one notebook with his own shorthand and codes that they still haven't figured out exactly what it is, how to break it up, how to read it all. And at least as of 3 years ago, that was the case when I was speaking to the archivist at IAS, and he was telling me about that. The papers included a proof of the existence of God that he did just to show that you could prove it, even though he didn't believe in God. And he didn't publish that because he didn't want people to think he believed in God. Okay, just for the historic environment in which this came out, there were all kinds of things that added uncertainty to the world. Einstein published general relativity in 1915, Heisenberg's uncertainty principle in 1927, Gödel's incompleteness in 1930. So in that short period of time, everything was brought up to doubt. Large-scale physics, small-scale physics, mathematics. And you could throw in there, even though it's not related to mathematics, the 1929 stock market crash. Okay, let me just add a few conclusions, comments on the proof and some of the conclusions to draw from it. One, it twists the liar's paradox around. The liar's paradox was this statement is false. A key part of Gödel's proof is that this sentence cannot be proved. If it can be proved, it can't be proved. But he had to put it in build a whole framework so that really worked properly. And that's part of the difficulty of the proof. It uses recursive function, possibly for the first time. At least one book says he invented recursive functions in that proof. I don't know enough about recursive functions to say, and the history to say exactly who invented what. It uses basic things about the integers, like the factoring of primes into, the factoring of integers into a set of primes uniquely. It uses a diagonalization argument similar to the one that Cantor used in proving that the cardinality of the reals is greater than the cardinality of the integers. And it is not a constructive proof. So to some who are constructivists, it's not an acceptable proof. It shows there is a sentence that cannot be proved to be true or false, but does not show how to find one. And in fact, it is hard to find specific ones. It's very hard to prove something is one of these undecidable statements. A few have been done. The only one I know of offhand is something about Ramsey theory that was proved by Harrington in the 1980s. I think there are a couple of others, but it's very hard to just take a statement and say you want to prove it's undecidable. And that leads to the question, are the famous unsolved problems undecidable? Can you prove that in them? I'm sure that mathematicians have tried to prove things like the Riemann hypothesis are undecidable. I don't know if anybody's made progress on the standard unsolved problems. And a couple more interesting things that follow that aren't always brought out. I think they assume that mathematicians will figure these out, but if you have a sentence that can't be proved true or false, an undecidable statement, then either G or G plus, or the negation of G, and I'm not sure if I'm using this explanation point properly in current syntax, but either the statement or the negative of the statement can be added as an axiom, because you can't prove it true or false. So it could be an axiom. Okay, that's sort of what the first conclusion. But then if you add that as an axiom, you still have a structure that has the arithmetic as the basis, and Gödel's theorem applies, so you can get another one, and you can get another one. You can add an infinite number of additional axioms. But will any of those additional axioms prove the things that you're trying to prove? Well, it's not going to prove everything, because Gödel's theorem will always apply and there'll always be another one. So you're never going to be able to make it complete by adding all these extra axioms. And some have conjectured that there are more undecidable sentences than provably true or false sentences. So maybe these undecidables are really most of what's there. But I haven't seen any proof of that, but that has been conjectured. Okay, one last thing as part of the lecture, then we can go to just open discussion. As I mentioned earlier, Paul Cohen in 1906 proved that the axiom of choice and the Cantor's continuum hypothesis are independent in ZF theory, Zermelo-Frankel. That goes along with Gödel proving that they were consistent. So if they're consistent and independent, that means that, that they're independent. That means if they're independent, they can't be proved. So therefore, they are these undecidable things. So you now have that in set theory, not in arithmetic, but in set theory, you've got these two statements that have been proved to be undecidable, and therefore you can add them freely as an axiom if you want to. And most mathematicians want to add the axiom of choice, so that's why it's referred to as ZFC. That's the axiom of choice. Because the axiom of choice is really useful. I don't know of anybody that's tried to add the continuum hypothesis. It might be, but in some domains, but I've never seen that. And the interesting aside is that Cohen won the Fields Medal for this work. The Fields Medal, for those that don't know, is only awarded in mathematics every 4 years, It used to be considered the equivalent of the Nobel Prize, but now there's another prize, the Nobel Prize. So both of them are claimed to be the equivalent of the Nobel Prize. But the thing about the Fields Medal is that only every 4 years, even though they can award a few, but you have to be under 40. It's meant to encourage young mathematicians. Okay, the first Fields Medal was in 1936, before Gödel's work was published. But there were no awards in 40 or 44 when he was eligible. Since he was under 40 in those years, maybe he should have won it then. That's just a closing comment on that. Okay, now come the things that can be open to discussion. I'll just list a few things that I'll leave this on the screen, that people have conjectured based on this. And they're really points of discussion because these are not things that are answerable with proofs. And I'll just list them. Does the fact that a statement cannot be proved false mean it is true? Are there true things that can never be proved? This is really the heart of many of these arguments, that people claim that there are true theorems that will never be able to be proved. So that is a different view of truth. Is truth different from provability? And that's one that philosophers like to discuss a lot. Are there then the other thing is connecting it to the brain. What does it say about the human brain? And there have been a lot of speculations about what you can say about the human brain, and they're really philosophical discussions. One argument is that anything algorithmic, including AI, would really be essentially acting in a space with the integers or the numbers. It's arithmetic. If you have something that's algorithmic, then it can't be as good as the human brain, which can conceive of things that might be true, even if you can't prove them. Again, these arguments, they're wordy arguments. They're not things I want to take a position on. Roger Penrose went so far as to say that there must be more to human thinking than can ever be achieved by a computer. Roger Penrose wrote The Emperor's New Clothes, which was an interesting book about the fallacies in AI about 20 years ago or so. Gödel, in a 1951 unpublished lecture, said that either the human mind surpasses all machines, or else there are a number of theoretic undecidables for the human mind. So in other words, either the human mind is better, or it's going to be things it can't figure out. One, I don't remember who said it, I just read this a few years ago, and I remembered it. They said that Gödel's theorem implies there could be no perfect antivirus. That one I would kind of doubt. And the last thing I'll mention is that John Barrow, in the paper that is in the references, says that since physics uses mathematics, and the mathematics has things that can never be proven true or false, then those are things that we will never be able to figure out in physics. Then the whole paper actually argues against this. But you'll have to read the paper, which is in the references, to figure that out. So at this point, I don't have a specific time limit. I will stay around as long as needed to answer questions about the talk or join in discussions about these unknown things, I guess.
Okay, so we're ready for questions and answers.
Yes.
That was an amazing talk. It really put all of the history of mathematics together and in a way I've never seen before. So I really appreciate that.
Well, actually, I hadn't seen it before, but I was just thinking about how to build this talk and what was he doing and why was he doing it. I started thinking back of what I knew about mathematics. So, the early parts of it, you won't find that in any of the references because that's just smattered from things that I've learned about mathematics over decades. And things from when I was even in undergraduate, epsilon delta. I never thought about that again, but I just started reading history and pinning down, where did epsilon delta come from? Just web search. Okay, hey, that was Bolzano.
Okay, our first question is from Al Aho. Would you please unmute yourself? Or you're unmuted already.
I'm unmuted. Bill, a terrific talk. I loved it. There's one issue that I have. The term undecidable in theoretical computer science means something different than the way you use the term undecidable. Is the term undecidable in logic what you claim it to be, that a statement is a paradox?
No, it's not a
Is
paradox.
that, or is that your own term?
I more or less use my own term.
Oh, then I would suggest that maybe you could find another term, because it confuses the hell out of theoretical computer scientists
well,
like me.
Okay. Well, that's the problem with anything. Words have different meanings in different contexts. I just wanted to stop having to, I started writing statements that can not be proved true or proved false. So I just call them undecidable. That's my own phraseology. If anyone has a better phrase, at first I was calling them Gödel statements because Gödel statements are undecidable, but that's got a more specific meaning. It's one that actually comes out of Gödel's proof. And I didn't want, I actually just changed that this morning away from Gödel's statements, because I knew that wasn't accurate.
Well, my question is related actually to your use of the term algorithm. The term algorithm, as it's used by most computer scientists, is a method that is guaranteed to halt on all inputs. It's related to recursive functions. A Turing machine that halts on all the inputs computes a recursive function. If the Turing machine need not halt on all inputs, it computes a partial recursive function. And sometimes the term procedure is used for a method that doesn't have to halt on all inputs. So when you use the term algorithm, what is your definition of algorithm? Does it have to halt on all inputs?
That is not the definition I was using. And in the early, this is going back to what they were talking about with Hilbert's program. Okay, and so again, I was not thinking from the detailed computer science perspective of requiring halting. And in fact, Turing's theorem basically says there isn't one, that there isn't a general one to testing it. But maybe I should have just said method. Some of the books that I looked at actually used that phrase, and I did not step back to think about what a computer scientist means by that phrase.
In computer science, the simple definition of an algorithm is just a Turing machine that halts on all inputs. You may not, or you can think of it as a recipe for doing something.
Right, a recipe that doesn't always work, or doesn't always stop. I understand the difference. I was not using it in the sense of a computer scientist.
Well, this gets to the fundamental issue of what is an axiom system, or more fundamentally, what is a proof in your world? What is the definition of the term proof?
I think I said at the beginning that I'm not a Gödel scholar, and this is not the area of math I actually worked in. I'm presenting history. Proof theory was another topic that was discussed a lot in the Vienna Circle, and Hilbert did a lot on proof theory. And it's just basically a way of having a formal language that lets you combine the axioms and the inference engine, etc. But I'm not at all an expert on that. So I was more of a mathematician at a higher level than that, so I didn't worry about formal proofs. I just went for proofs that I thought were correct.
The reason I'm interested in all of these is that the first course I took at Princeton when I went there for my PhD was from Alonzo Church.
No, yes.
And Alonzo Church was fond of precise definitions. So he instilled that on me. But it's also related to, if we want to have a sound and consistent theory for mathematics, we need precise definitions. And sometimes as you pointed out, if you take sloppy definitions like naive set theory, some strange inconsistencies can arise.
No, I fully agree with what you're saying. And in mathematics, you definitely do want very precise definitions. And when you're not precise enough, then you get into trouble. But I also preface that this is not my area of expertise. And if I misuse some of the terminology that was, in essence, taken from some of the books that I was reading that were not necessarily written by computer scientists, I'll plead guilty.
But in any event, congratulations on a brilliant talk.
Yeah. What my point was really trying to get to the thread of history and how it led to what he did, and that he was not just a one-hit wonder with the one theorem. He actually did a number of other things that are important. And
Another anecdote, for my PhD, I took 6 courses from the Princeton math department, and I didn't realize what a treat that was and how brilliant these people were until long after.
that's probably always the case. When you're too young, you don't really appreciate it. I mean, I didn't fully appreciate what this meant. I said, hey, that's a neat little thing. Maybe some of these unsolved problems can't ever be solved. Okay, fine. Next thing.
Anyway, thank you.
So Al, in your coursework, did they ever go through the proof of Gödel's theorem, incompleteness theorem?
Yeah, yes, I did. I took a course on recursive function theory.
Okay.
And I agree with Bill that it's not a proof that you want to present to the general public.
Yeah, I bought the one book, Gödel Without Too Many Tears, which is goes through the proof, and it's quite daunting actually. But
You may have heard the term Gödel number.
yes, I have.
Gödel numbering is often used in computer science proofs, theoretical computer science proofs.
Okay. All right, Paul, can you tell us if there's any questions from the audience?
There's no audience left except me.
I see. Do you have any questions?
Okay, I have a question. It's not about the mathematics, but you may have said this along the way, Bill, but you started off by saying that Gödel's proof is too involved and you're not going to go through it in today's session. But I think you also said, or Walt mentioned, that you've been reading recently some books about Gödel. So the question is, have you been through his proof? And were you able to follow it? Is this something that an ordinary mortal with a PhD in math can actually follow? How long is it?
Well, the book that Walt just mentioned has an overview of it, and I think 50 pages, then the rest of the book does it in detail. My exposure to it was about 4 or 5 years ago. I took an informal, non-credit 4-week course in Gödel's work. And in the course of that, they developed the mechanism to be able to outline the proof. And I was following, but at times I got bored and didn't follow it completely. So yeah, I've seen it, and I would not be interested in going through it in detail. But I have seen it presented, but it was over a couple of lectures, and I didn't always have all the threads connected. And I got the general flavor, but could not reproduce it. Because there's so much mechanism you have to put together before you start proving it. All the proper definitions of things, which I admit to being sloppy with. Just trying to give a vague sense of what was meant, not the. I gave this talk, let's say, as a historian, not as a mathematician, but I included things I remember from when I was a mathematician.
Okay. Do we have any other?
We actually have two. We have 2 audience members who returned.
Oh,
You guys have any
okay.
questions? They're not raising their hands.
Bill, before you go, perhaps do you have any thoughts on the church Turing hypothesis, church Turing thesis, that any function that can be computed by a Turing machine? And if you believe that human beings are biological computers, then we can be simulated by a Turing machine. Any thoughts on this line of reasoning?
No, that's not an area I know enough to have thoughts on. I know what it is, but have not really thought about it. No thoughts, but I'd be happy to hear your thoughts about it.
The issue about the human brain, I think of it as a distributed system that maintains an ongoing, distributed computing system that maintains an ongoing interaction with its environment. Whereas if you look at a Turing machine, it just computes a function, it's sequential computation. But my very, very limited understanding of how the human brain works is that there are all these thoughts raging inside the brain, and somehow or another, the operating system of the brain decides which thought becomes foremost. Nobody really understands the algorithm or the working of the human brain. Whether we ever will is an open question, but it's a marvelous computing device. And I think there are a lot of interesting open questions associated with this. And the whole area of artificial intelligence and machine learning gets at the difficulty of really understanding what can we achieve with computation.
Well, I have a question about that. So we've been talking about the human brain and how intimately the structure of the human brain might be related to these theorems and all this mathematics. But what about a non-human brain? What about an intelligent being on a different planet in a different solar system in the universe, and a totally different brain? Is that going to be this basically equivalent to the human brain because there's only one way to build a brain, essentially, or even on the Earth? I'm told that octopuses have a very different kind of intelligence. They're quite intelligent, but their brains are organized very differently from humans. No takers.
Well, I have read that the octopus actually has a satellite brain in each of the tentacles. So that's a very distributed system. But anybody have thoughts on these questions? But I mean, the thing about the Turing thesis, it relates to, can an AI ever be as good as the human brain? There's a relationship there that
Well, the only thing I think that could be close to it would be like the AlphaGo system, which has, multiple processes going on that interact with each other and can learn, the game of Go better than a human can. Basically with unsupervised learning. I think that's the closest anybody's come, as far as I know. Now, I saw Thad Gabara raised his hand. Are you still there?
Yeah, can you hear me?
Yes, we can.
All right. Yeah, what was your comment, Walter?
Now I just mentioned about, AlphaGo, which is the game that Google has that plays the game of Go. But I noticed you had your hand raised before. Did you have a question?
Well, yeah, it was the issue about Gödel's proof. And I found, I was reading the book Gödel's Proof by Nagel and Newman. And got to the end, and that's where it lost me. But, this is on my bucket list to go back and reread this and see if I can figure it out. but I love the way that he approaches the problem by turning all of the mathematical laws into a set of prime numbers, essentially a prime number, or multiples of prime numbers. And then you can always extract back what that original equation was. And but there's a point where I got lost, but it's on my bucket list to try to figure it out. A great talk, by the way, too.
Thank you.
John,
I mentioned philosophy, implication of philosophy earlier. I never really put up any slides, but when I was a student and I was doing this, I was talking to a friend who was a philosophy student, and I said, it's amazing. There's proof that there's things that are true that we can't prove are true. And she said, well, in philosophy, we always assume that.
so John Maheda, do you have any questions?
Not really. I'm still trying to digest what I heard.
Okay.
Well,
about Fred?
anybody have thoughts about the idea that the brain can actually think of things and somehow think know they're true, but not be able to prove them? And that's sort of what some of these conjectures are saying. Penrose and the other one saying that AI is not as good as the brain because the brain can somehow think of things that would be true, but Gödel says that they're not true, or that you can't tell if they're true. I mean, is there something in the brain that has an ability to decide something is true without there being a mathematical proof? I mean, that's just a notion that doesn't make sense to me, but how would the brain know that? But that seems to be the base of some of these arguments, particularly Penrose's. There's got to be more to thinking than can ever be achieved by a computer. I mean, his whole paper is much longer than that, obviously, but that phrase was short enough to put on a slide.
Well, I did read the book on one of his books. I think The Emperor's New Clothes, I think it was.
Yeah.
Or maybe it was one of the other ones. And I think he mentioned something that maybe the human brain uses quantum computing to do what it's doing.
It's quantum mechanics, not quantum computing.
Well, okay, quantum mechanics.
At the atomic level, everything is quantum mechanics, and there's always randomness in quantum mechanics. So one of the conjectures that I don't think applies here is that the brain does have these random thoughts, and maybe that's how we get brilliant ideas. But that having a brilliant idea, like it's like the twin prime problem, is not the same thing as knowing it's true.
Mm-hmm.
That would, to me, that would be a way of giving you something to strive to do. You might get this flash that, oh, what about this twin prime thing? And you might think it's true, but then you have to go out and prove it. So I sort of don't agree with most of these things, but I'd like to hear anybody who's thought about them and does agree with them. But you're right. The quantum bit and the human brain is something that has been considered as being the source of new ideas. But again, there's a difference in getting the idea and thinking it's true and then proving it's true. And is there some way of saying that some of these ideas really are true and we think they're true, but we still can't prove them? That's the one I have my doubts about.
Now the question I actually have is, some of these things that can't be proved are difficult because they go out to infinity. So I'm wondering if the fact that they go out to infinity is the reason for them not to be proved rather than Gödel's theorem.
Oh, you're saying the proof would be an infinite number of steps?
Well, I did the talk on the 3x plus 1 problem, and
right.
They've gone out as far as they can numerically. And I sort of looked at it in more detail. I says, well, this really ought to be true, but it can't be proven. But maybe the problem really is, if you can't deal with the infinity aspect of it, maybe that's the reason, and not something like Gödel's theorem.
Oh, I mean, the infinity aspect, there's an infinite number of steps you could take. And if you, all you need is one counterexample. So maybe you have to go out, you know, 1,000,000 years of computation with the highest speed computers, and have to go through all the problems, and then you're going to find the counterexample.
Well, if a counter example can be shown, then
Right.
everything is set. But
But if,
until you can show that, you kind of have to assume it's true, you know.
well, I wouldn't do that. It's not mathematical, and maybe it's you could say it's true for all numbers less than, you know, 10 to the 10 to the 10 to the 10th, whatever space you've computed on, but there might be one after that.
Okay. Well, since it doesn't look like we have any more questions, I want to thank Bill for a really great talk. You know, I've learned a lot about the history of mathematics in areas that don't get generally taught in any coursework I've taken. And so I hereby conclude the Math Interest Group talk. So thank you, Bill.
Thank you.